Hello, my name is Neha. I am a graduate student at Berkeley, and I'm going to tell you now about some work I did as an intern at Google Brain with collaborators Daniel, Sam, Ethan, and Joshua. So today we're going to be interested in thinking about the effect of either whitening the data or using a pure second-order optimizer on the ability of a trained model to generalize. Everything we've done is written up in a paper that's posted to the archive, and I have a link to that on the very last slide. So the first result that we prove is that for models with a fully connected first layer, the only information SGD or full batch GD can use to generalize is contained in the sample second moment matrix, also known as the gram matrix of the data. Our second result is that whitening diminishes the information in this matrix, and in particular in the high dimensional setting where you have less data than the dimensionality of any given data point, whitening completely destroys the information in the gram matrix. If you put these two results together, you get the prediction that whitening should negatively impact generalization in a dimensionality-dependent manner. The second theme of our work is that due to a known equivalence between training with Newton's method on unwhitened data and SGD on whitened data in linear models and therefore also in overparameterized networks, we expect generalization in these models to be similarly negatively impacted. The key takeaway of our work is not never whiten or use a pure second-order optimizer. Instead, the key takeaway is that whitening and pure second-order optimization always throw away information. If you're dealing with a high-dimensional data set and intend to train with SGD, it's better not to whiten your data. Pure second-order optimization never generalizes better than SGD. However, it's always faster. If you regularize your second-order optimizer, you can sometimes have the best of both worlds, where you both generalize better than gradient descent and train faster than it. So here are some experiments. In green, we look at the generalization performance of models trained with gradient descent on whitened data, and in purple, we look at gradient descent on unwhitened data. In the top left, you can see that in a linear model, gradient descent on whitened data underperforms gradient descent on unwhitened data. The vertical dashed line indicates the input dimensionality of the dataset. You can see that generalization begins to recover in the whitened case when the size of the dataset gets larger than the input dimensionality. The pink circles indicate the performance of Newton's method. You can see that it is indistinguishable from gradient descent on whitened data. On the top right, we're looking at a 3-layer fully connected MLP learning to classify CFAR10. Once again, you see a similar result, which is that gradient descent on whitened data underperforms gradient descent on unwhitened data. On the bottom panel, the two figures are for networks that are not treated by the theory that I talked about earlier. So on the bottom left is a wide residual network, but once again you see the same result, which is that gradient descent on whitened data underperforms gradient descent on unwhitened data. On the bottom right, we're looking at the performance of the Gauss-Newton method in pink versus gradient descent in purple, in both cases on unwhitened data in a convolutional network. What you see is that even though Gauss-Newton method often trains to lower values of the training loss, at the same time it often has higher values of the test loss, which means that it generalizes worse. If you regularize your second-order optimizer, the form of the regularizer we used in this experiment is given at the bottom of the slide. If you regularize, then you can see in the left panel that for some values of the regularization strength, lambda, the Gauss-Newton method actually performs better than gradient descent. And on the right-hand side, you can see that Gauss-Newton is always faster than gradient descent as measured by the number of training steps to best validation performance. So here is an example of a situation where you can have the best of both worlds. So with that, I'd like to say thank you. Here is the link to our archive paper. I'm very happy to answer questions in the discussion, and also please feel free to email me. Always happy to chat.